Hi everyone, my name is Joseph Noyd, and today I would like to present my final project for EE210. I decided to design a driver machine logic board as I believe it allows me to demonstrate all the concepts that we learned throughout the semester in switching systems. I've used a program called logisim to create and simulate the logic board. This driver machine design I intended to be used in a household application as it is free of charge. In the first part of the presentation, I'm going to walk you through the normal operation of the circuitry and explain all the safety features I built in. In the second part of the video, I'm going to talk more in depth about how the circuitry works, what are some interesting features of it, and some limitations of the design. But without further ado, let me get into demonstrating how this driver machine actually works. So I'm gonna walk up to my brand new driver machine that just got installed today. I'm gonna press the power button. It's on. The 7-segment displays turn on, as well as the LED light in the bottom corner indicating that the machine is indeed on. After that, I'm gonna open the driver's door to load in my clothes. Clothes are loaded in, then I close it. After that, I adjust the timer to 40 minutes. Next, I'm gonna select high heat to start the machine. I press it. We can see that the motor's power indicating light turns on as the machine is started. It is not shown in this design, but this part of the circuitry could be connected to an analog circuitry operating the drive machine's motor and heat intake. While the machine is running, I look down and it looks like I dropped a piece of sock on the floor. So I open the door to put the sock back in the machine. And as we can see, while the door is open, the machine stopped running, and the only way to start the machine up again is to close the door. So I do just that, close the door, the machine is running again. When I close the door, I also want to change the heat setting to low heat. So I press the low heat button, and the heat setting is changed to low. When the timer reaches 0, the cycle is finished and everything is reset to starting position, allowing the user to start a new cycle. Let's test this out. This time I'm going to adjust the timer to 20 minutes. On here, I would like to demonstrate what happens if I keep adjusting the timer by 10-minute increments. If I go over 90, the timer resets back to 0. So let's just go with 20. And I start the machine this time on low heat setting. We can see that the machine completes the cycle as desired. In the following part of the video, I'm going to demonstrate some safety features that I built into this circuitry. Let's say I have a cat that likes to play with random buttons on machines, and he or she presses the buttons of the driver machine in a non-logical sequence. Buttons are programmed to only be pressed in a logical sequence, such as the circuitry doesn't allow me to press any button before turning the machine on. Let's test this out. So I'm going to turn the machine off. It's off. I'm going to try to press any button. They don't work. They are all disabled. Except for the door, I still be able to open the door. Also, before selecting the duration of the cycle, the heat selector buttons are disabled, and let's see this. So I turn the machine back on, and I want to start the machine right away. It doesn't let me. These buttons are disabled. I can only start the machine after selecting the duration of my cycle. If I turn the machine off mid-cycle, turn it back on, its memory resets, and we are back to starting position. So let's see what happens. I'm going to start the machine, it starts down counting, and I turn it off, turn it back on, machine is at starting position. And now we reach the second part of the presentation where I would like to give you an in-depth tour of the logic board. I'm going to go clockwise, showing you each of the sub-circuitries and explain what they do and how they are part of the system. Upper left corner, we have a double-digit 4-bit down counter. Each of the counter uses 4 JK flip-flops. Let me show you inside. LSB is responsible for the least significant digit of the display. MSB drives the most significant digit. Since it's a synchronous down counter, MSB's flip-flops enable pins only receive high signal when LSB is exactly 0 and the machine is on. Let me show you this. The timer counts down. LSB reaches 0. It sends signal to MSB's input pin. and it also sends high signals for MSB's flip-flops enabled pins. The clear gate sub-circuitry in the upper right corner is responsible for sending high signal for MSB's flip-flops clear pins at the right time. This is how it looks inside. Then we have two 4-bit decoders hooked up to the down counter. They decode binary input to 0 to 9 decimal output, and this is how they look inside. They are just duplicates of each other, so the other one will look the same. Next, I'm gonna show you the sub-circuitries that drive the 7-segment displays, starting from left to right. The following sub-circuitry, the 4-bit adder, is technically a 0 to 9 up counter. It is responsible for presetting and clearing MSB's flip-flops when the user is adjusting the time by 10-minute increments. It has 4 JK flip-flops and 1 D flip-flop. The D flip-flop is there to send signal to the system, whether the user set the drying cycle's time or not. And lastly, the heat selection sub-circuitry. This sub-circuitry has 4 outputs. It tells the system whether heat was selected by the user, whether the machine should run on high or low heat, and also whether the operation of the driver's motor should be enabled or disabled. It has 2 JK flip-flops and 1 D flip-flop. The JK flip-flops are responsible for sending signal to the system whether high or low heat was selected. The D flip-flop is there to send signal whether heat buttons were pushed at all. In conclusion, I would like to say that designing this logic board was a very exciting project for me. It does have some limitations, such as being able to add time while the machine is running, but I believe it would require deeper knowledge in switching systems to implement that design change. I would like to thank you for watching my presentation. If you have any question, please feel free to leave it in the comments.